today? Wednesday. Following Monday, we're going to go over some problems and some former problems that you have been assigned, plus the new homework with our GA location. So you can be there on Monday. And then Wednesday, we're going to do a test. It's not a midterm test, it's just going to be a test. It's going to be a test on the notes we've had so far. Okay? Sound good? So, not this Wednesday, the following Wednesday. It's lots of time. And I'm going to try to give you guys lots of preparation so that you feel very confident about how to do it. Okay, so try to finish up the second section of the intro notes are some of the algorithmic techniques. So as an example is, let's say we wanted to find out the average depth of a binary search tree node, average depth. Before we do that, what is the depth? Depth is basically measuring how far a node, like any of these nodes, is from the root. So the depth of this one is 0. Because it's the same thing as the root. This one, what's the depth? How about this?
1.
How about anything here?
3.
Okay, you got it. So to find the average depth, all we have to do is add 3 plus 3 plus 3 plus 2, 2, 2, 2 plus 1, 1 plus 0, and divide them by the number of nodes. That will give us the average depth. Okay, now, we're going to make an assumption to make things a little easier for us because this is not a general problem, but specifically we would like to know if we look at a tree like this tree we describe to be full, F-U-L-L. Full means that every level has the maximum number of nodes it can have. So since this tree has how many levels? 1, 2, 3, 4, also known as height, okay? The height is 4, and every level is fully filled. So therefore, now, technically speaking, we're going to say this has really 15 nodes because it's 8 plus 4 plus 2 plus 1 is 15. We're going to say 16 is very close to 2 to the k minus 1 is very close to 2 to the k. So we can say n is 16, k is equal to 4, where k is the height of the tree and n is the number of nodes. So what we can try to do is we can try to set up some type of a way to sum all those nodes. And to do that, there are two different approaches. So approach number 1, I'm going to skip. I'm going to go directly to approach number 2, because either one of them is going to give you a very close approximation. So one look at that way. One way of looking at that is to say, look at the picture of the tree and see what's going on here. Well, what's going on here is that the number of nodes is doing what at each level? What's going on with the number of nodes? 2 goes to 4, 4 goes to 8, 8 would go to 16. So what's happening with the number of nodes? It is doubling. Okay. So doubling, well, doubling means that it's times 2. Well, so whatever number we had before, the next one is times 2. And whatever we get there, the next one again is going to be times 2. So basically what we have is 2 to the 0, times 2 is 2 to the 1, times 2 is 2 to the 2, times 2 is 2 to the 3. And the next time we'll get 2 to the 4. So basically the number of nodes is going up exponentially with a base of 2. However, the depth is not, so what's the depth here? 0. How about here?
1, 2,
3. Next one will be 4. So the depth is increasing only plus 1, plus 1, plus 1. So if I is the depth, then I is 0. But the number of nodes is 2 to the I, which is 2 to the 0, which is 1. When the depth goes to 1, it is, now I goes to 1. And the number of nodes is 2 to the 1, which is 2. So you see the pattern we're getting? Next one we have I is 2, and the number of nodes is 2 to the 2. So in general, when the depth is I, the number of nodes is 2 to the I. That make sense? Okay, so the second model simply says, you see, so this is the depth, number of nodes. This is the depth, number of nodes. Depth nodes, etc. So in general, since the height of the tree is k, we notice that the height is k, which is, in this case, which is 4. So this is going to be 1, 2, 3, 4. But notice that in our summation here, notice that we stop at 3. So instead of going 1 to 4, we go to 0 to 3. Well, that tells us how we should structure our summation. So the summation should start at 0, go to whatever is 1 less than the height of the tree. Since the height is k, it's going to go to k minus 1. So, and again, I 2 to the I 2 to the I 2 to the I like that. So therefore, we have the summation is simply, as I goes from 0 to k minus 1, I 2 to the I. Notice that I can change the bottom index to 1. Why? Because when I is equal to 0, it's 0 times 2 to the 0. Doesn't add anything to the sum, so I can easily just move that index to 1. Because 0 produces 0, and it doesn't change anything. So, now, so we are going to, we know, or at least we will know today later on, that the summation of I 2 to the I, as I goes from 1 to k, is going to equal to k minus 1 times 2 to the k plus 1 plus 2. That's the result we're going to get later on today, but that's the result I'm telling you. Trust me on this one right now, and we'll come back to it. So therefore, since if this is in fact the result, then k could be anything we want it to be. K could be 3, 4, 8, 10, 100. Well, I want k to be k minus 1. Well, if k is k minus 1, then substitute k minus 1 for k, and we're going to get k minus 1 minus 1, k minus 1 plus 1, plus 2. So that's the result. So what we get here is the summation that we're trying to get is equal to k minus 2 times 2 to the k plus 2. Now, what we're going to do is now what is k again? K is the height of the tree. However, we're more interested in the number of nodes. Okay? The number of nodes is equal to approximately 2 to the k. 2 to the k minus 1 or 2 to the k. It's only a difference of 1. As k gets bigger and bigger, that minus 1 is nothing. So what we're going to do is we're going to replace 2 to the k can be written as log of 2 of n plus 1 minus 2 times n plus 1 plus 2. So 2 to the k is 2 to the value of k. And what is k again? Log base 2 of n. So therefore, so this, converting it from k to n, gives us this results. Okay? And so that's our result because n is approximately 2 to the k minus 1. So therefore, the average depth of a node is going to be all of this stuff divided by the number of nodes. Okay, any questions about this? How we go from, so this is a result I'm asking you to just use, and we'll come back to it, we'll derive it, and this one is just substituting k minus 1 for k. Okay? Okay, so what I did was, I took this formula that we came up with, the average depth of a full binary search tree node, and of course the number of nodes, so we use 15, 31, 63, this is always 2 to the k minus 1, and I went all the way up to about 64k, so 2 to the 60th power nodes. And if you look at them, this is what of the tree? Height of the tree. And this is the average depth. Look at the average depth. So the height of the tree is 16. The average depth is 14. What is the depth of the deepest node in a full tree? Here. When the height is 16, the depth is actually 15. Right? Because remember, if the height is 4, the depth at the beginning is 0. Is 1, 2, 3. So therefore, if we have 16 is the height, then the root is still 0, so the bottom level is 15. So the deepest leaves are at depth 15, but the average depth is 14. Does that surprise you? Did you think it was going to be something between 0 and 16, something more like 8 maybe, right? But it's not. How come? Because the number of nodes doubles as we go to the bottom. And if you think about it, let's think about this tree. Let's look at the tree of height 10. So look, tree of height 10 begins like this. So at height 1 or depth 0, right, it's going to start with 1 node, then 2. 1 plus 2 is 3, it's called 4. The next level has 8. Okay? 8. So we have 8, what do we have before? 7. It's going to be 15. Let's call it 16. The next level has 32, which makes a total of 63. The next level has 64. So the level at the bottom has one more node than every level above it. So if we go to, just if you look at this, if you look at 10, then how many nodes are in the tree which has a height of 9? Well, 511. But in order to look at the height of 10, I have to add how many nodes? How many more is this than this? 512. So what happens is as you add, so that means that 50% of the nodes are at the deepest possible level. Okay? So it's very, very interesting. So it shows you that the big takeaway here is that I want you to recognize the fact that the average doesn't always fall in the middle. Adding the top and the bottom and say that's the average means nothing. That's only the average if both of them are equally likely. But it's more likely, for example, what is the probability that a node in a large full binary tree is at the deepest level? What's the probability of that? It's almost 50%. It's just about 50%. In fact, it's a little bit more than 50. Because it's always one more node than everything else above. But basically speaking, as n goes to infinity, as the number of nodes grows, and the tree stays full and balanced, the probability of being at the bottom level approaches 50% exactly. What's the probability of being one level above the bottom? For large, full trees. Well, you got about half the nodes at the bottom. What's half of half? Here. So you got about 1 out of 4. Right? 25% of the nodes are going to be a second to worst level in terms of depth. So 50% at the bottom, half are going to be at the bottom, a quarter are going to be 1 minus the bottom, an eighth are going to be 2 minus the bottom, a 16th, a 32nd. How many are going to be at the root? 1. So if you have 1,024 nodes, what's the probability that a random node is the root? 1 out of 1,024. Okay? So the probability that you are high in the tree is low. The expectation is that you are, on average, going to be 1 level less than the deepest depth, because of the way the tree grows. And that is an interesting question. I might ask you something like this on a test. Find the same proportion for a tree that is a 3rd degree tree. So we have a root, 3. Each of the 3 has 3, which is 9. Each of those 9 have 3. So the tree is growing not 1, 2, 4, 8, but it's growing 1, 3, 9, 27, 81, 243, 729, etc. It's growing like, so it's getting even wider. So where is the average depth? That's a problem you might want to solve. Or at least think about. Okay? But again, we need to have some mathematical tools, and that's what we're going to be working on. Okay. The binary search approach. I think we kind of already did that. Why am I doing that? I thought we did that. Let's see. I don't care about the iterative approach. No, I'm not going to care about that, so I'm going to skip that. I think that's pretty much going to cover us through these notes. Okay, so let's go to the next section. So the next section is part 3, and part 3 is going to be, here. This is the area I like it here. Before I do that, let's see if I can do this right here. Okay, so what I'm going to do is just go through this, and this is actually up on, I just put this up here just as a review because we're going to need to know how to take some derivatives, some simple derivatives, nothing too fancy. We don't have to worry about sines and cosines and tangents and cosecants and all that kind of stuff. We don't care about that. But we do care about polynomials. And polynomials are fun because they're easy to use calculus on. So the first thing is, so we have here, so again, this is going to be x to the n power. What does this little dash mean? That's the derivative, okay? That's the derivative. So x to the n power derivative means the derivative of x to the n with respect to x. X is the variable. And so the n is going to be any constants. For example, it could be x to the third. So if x is x, if it's x to the third, then the derivative will be 3 times x to the second. Yeah, if n is 10, it's going to be 10 times x to the 9th. Okay, if n is 5, it's going to be 5 times x to the 4th. Get the idea? Now, if I have a polynomial and I have, let's say, two terms, like x to the third plus x to the second, the derivative of x to the third plus x to the second will be 3 times x squared, and then you add the derivative of the second part. So the derivative of a sum is the sum of the two derivatives. And they're very easy. Just take the exponent, multiply it by x, and knock the exponent down by 1. That is the general power rule for derivatives. Okay? And it's easy to do for this. Okay, now, a lot of times in computer science we're going to find algorithms that have some type of a log. So ln x, and we're going to find out all logs are proportional actually. So it's not that important. And I will have a little bit more notes on these derivatives as is necessary. Okay? And you certainly can use them on a test. If I give you a test, you certainly can use that, so you don't have to memorize any of these things if they're not easy for you. And of course, I'm not going to give you anything that I haven't tested out on you in class. So if you scream and yell at me in class, then I'll explain it. But if you don't, I assume you're getting it. Okay, so if I have to take the derivative of the natural log function, natural log of x, that is simply going to equal to 1 over x. 1 over x. If I take the derivative of an exponential function, which is, by the way, the inverse function of this, e to the x, the derivative of e to the x is, mistake here, should be e to the x. So this derivative should be the same. This should be exponent here. My bad. Now, if I have k to the x means that it's not the natural base e to the x power, but it's some other number like 2, 3, 5, 7. So if I have some other constant k to the x power derivative, it's going to be, the derivative is going to be k to the x times the natural log of the base. Okay? So the derivative of e to the x, e to the x. The derivative of k to the x, k to the x times ln k. Okay? And sometimes our functions, our complexity functions, will be products. For example, x log n, or x squared log n, or log n squared. There's a few other types of rules that I'll go over as we need them, but basically if you have a function which is a product of two functions, like for example x squared log x, then the derivative of this product is going to be the first one times the derivative of the second one, plus the second one times the derivative of the first one. And we'll be doing those things. And the last one on the bottom here, I do have the integrals, but I'm not going to bother going through the integrals now. I will explain them as we need them later on. So again, I will take these notes and I will be expanding those notes so you have them to use. All right, so let's get back to, where do you want to go to? I'm going to go here. Okay. Okay. So basic math stuff, we'll go from basic stuff to more advanced stuff. So a couple of functions here. One is called the floor function, one is called the ceiling function. The floor function takes, if you have a real number, it will be the largest integer less than or equal to x. Floor. So let's say you have a number like 2.8. 2.8. So you're going 1, 2, 2.8. So what is the largest integer you passed that's equal to 2.8 or less than that? 2. So 2.8 goes back to 2. How about if you go to 2.1? What's the floor? 2. Again, 2. How about 2.9999999? 2. I told you, I do it, I was lucky to get one person. So 2.99999, the floor is going to be, because we still didn't get to 3, so I want the largest integer less than or equal to. Not the one that's a little bit more. So it goes back to 2. So floor always goes, now what is the floor of 2? 2. What is the floor of -1? -1. Now here's the tricky one. What is the floor of -1.5?
One.
-2. Because you're always approaching from the left. So if you have -2, -1.5, you didn't quite reach -1, so you go back to 2. Not a big deal. I just do that mathematically because I'm obligated under the mathematical laws, but I don't think we have to use too many negative numbers in this class. Okay, now the opposite is true of the ceiling. Ceiling function goes up. Whenever you pass an integer, but don't quite hit the next integer, it goes up to that next integer. So, the ceiling of 2.999, 3. 2.01, 3, because you passed 2, now it's 3. The ceiling of an integer is just an integer. Easy stuff, right? All right, now, in terms of functions, logarithmic functions are quite interesting. This is what a logarithmic function looks like. Now, notice that I'm only showing it to you from 0 here. And the reason for that is because the function log of x is only defined for positive real numbers. It is not defined for 0, and is not defined for negative numbers. And you can see that this function is increasing. Increasing means that as I go to the right, I continue getting higher values. In fact, it is an increasing function because it is always getting bigger. Now, the derivative, which is ln x prime, also I can write as ddx. ddx is the derivative of ln x, same as I had ln x with a little prime mark, is 1 over x. And can somebody tell me what is the meaning of the word derivative as it relates to the graph? What is the meaning of a derivative of a function?
Is that the opposite of this?
No,
It's the change.
it's the rate of change. So it's the rate of change. In fact, another way of interpreting it is that the derivative, which is 1 over x, which I told you that's what it is also, for example, if I take the number 6, see the 6 over here? Tick, 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 tick. I hit it right here. If I draw the tangent line at 6, it will have the slope of 1 over 6. If I look at 16, and I go up here, the tangent line at this point to this curve will have a slope of 1 over 16. The slope, notice that the slope, as I go from 6 to 16 to 26 to 36, what's going on that slope? That slope is?
Decreasing.
It's actually decreasing. I had 1/6, 1/16, 1/26, but it's always positive. Slope is always positive. It will always be positive. Even if I go way out here to 100,000, it's going to be 1 over 100,000, which is very tiny, but positive. A positive derivative means that the function is always increasing. So that's why this function is always increasing, because the derivative is always positive. Now, even though that derivative is getting smaller values, it never is 0. It'll just get smaller and smaller, approach 0, but it'll never get to 0, so it's always positive. So the function is always increasing. Now, derivatives and integrals undo the functions. So if I have the derivative, ddx of natural log of x is 1 over x, okay, then if I take the integral of a derivative, it will give me ln x. Okay, so the derivative of ln x is 1 over x, so if I take the integral of ddx of ln x, it's going to equal to ln x. And that means that ln x is equal to the integral of 1 over x. You want to see it on the board? Okay, because it may be helpful. So I'll show you a couple examples. I'll do like a simple polynomial function, and then we can do the log function, just to see how that's going to work out. So let's say we have, So we have ln x. Can you guys see that? Okay, so now, so d dx ln x is the same thing as ln x prime I showed you before. The derivative with respect to x of ln x is the same thing of ln x prime. That's the same thing. This just says the derivative of this with respect to x. X is the variable. And we're always going to have one variable, and it's usually going to be x or n. Usually like that. So let me leave it like that. So that's equal to 1 over x. Now, when we take normally the d dx of any function of x, we produce a new function. Because the derivative of x squared is what? What's the derivative of x squared? 2x to the 1. What's the derivative of x cubed? 3x squared. What's the derivative of 4x squared? 8x to the first power. So if you, now, if you're a little shaken in that, don't worry about it. So basically, so if we have something like this, 3x to the 5th power, if you take the 3 away, what's the derivative of x to the 5th? 5x to the 4th. But if you have a coefficient, you can just say the derivative of this times this is this times the derivative of that. That's 5x to the 4 and 5 times 3, so you're going to get 15x to the 4th. It's almost like multiplying by this and then knocking the power down. Okay? So, so the derivative with respect to x of f of x is going to be a new function. So if f of x is equal, like I said, to 3x to the 3rd power, then the derivative with respect to x of this function will be what? 9x squared. Now, if the derivative of a function is a new function, then the integral of the derivative of this function will bring this function back up. So we have to be able to come back. So if we integrate this function, we're going to get back to this function. And so the way that works is it's opposite of the power rule. So what happens is if we have the integral of 9x squared, now we always have to specify, like just like we have d dx, here d dx, we put a little dx here. That means we're integrating with respect to x. That's all the dx means. So what happens here is, again, the constant can come right out in front, and so we're going to get 9 times the integral of x squared dx. And then to integrate the function, rather than decreasing the power, we increase the power by 1, and we divide it by the same value. So that's going to equal to 9 times x to the 3rd divided by 3. Okay, so, why is it not working out? Is it working? Yeah, it's working out. It's working out. So, what's 9 divided by 3? So that's going to be 3x cubed. Okay, let's do another simple integral before I finish that one. Let's take the integral of 3x to the 7th dx. So you can take the 3 out, and then what you're going to do is you're going to get the 3 out, you're going to take this and you're going to do what? Up the power, x to the 8th power, and you're going to divide it by 8, which is the same thing as multiplying it by 1, right? So the whole result is going to be 3/8 x to the 8th. Okay? So, if I have a function, if I take the derivative with respect to x of f of x, this is a new function. But if I integrate this with respect to x, what is the result of this? That's going to be f of x, because it's going to just bring this function back. So the derivative of a function gives me a new function, and the integral of this new function brings back the original function. So the integral of the derivative is the same, and then all the way around, the derivative of the integral is also going to be the same. Okay, so with that in mind, we have the derivative with respect to x is equal to ln x, which means that if I wanted to integrate that function, use the integral, and I'll give you very good reasons for using the integral, why it's important to us. If I wanted to integrate this function with respect to x, I can do on both sides the same thing, right? So they do the same thing on both sides of good. So this is just dx up here. So this is the integral of the derivative of ln x dx. So the answer, the result of this is going to be what? This is going to be ln x, right? Because we're deriving, producing a new function, and then we're integrating, bringing back the original function. So ln x is going to equal to the integral of 1 over x dx, which says that the integral of 1 over x dx is natural log of x. Now, why is this so important? It's important because, you might say, why is it important? Because we're working with discrete numbers. We don't have to worry about areas under the curve and things like that, and continuity. We have to worry about 0, 1, 2, 3, 4, 5, 6, 7. We don't have 2.5. You can't have 2.5 inputs. You have 2 inputs, or you have 3 inputs, or the input is 2, the input is 3, that's it. So that's true. However, sometimes it's very difficult to find the complexity of some discrete functions. Functions that only work on integers. But we have some ability to look at the calculus or the integrals, which are allowing us to find very tight boundaries for those unsolvable discrete problems. That's why it's important. Now, the other thing I want to kind of throw at you right now to make sure everybody's good on this, again, I'm not going to be explaining all this, but I want you to understand that it's absolutely true and it's absolutely consistent all the time. And that is, let's take a look at 1 over x. Just this function 1 over x. Let's see if you can imagine what this function looks like. So 1 over x, x cannot be 0, right? So this is going to be the y-axis up here. This is going to be the x-axis. So the y is here, the x is here. This is 0. This is the origin. So this function 1 over x is not defined here. But if I go to 1, what's the value of the function? 1 over 1 is? 1. And 1 over 2? 1 over 2? 1 half. And 1 over 3? 1/3. 1/4. 1/5. So so what's going on is this from 1 is kind of doing this. Okay? What happens when I go to 1 half? 1 over 1 half. It goes to 2. 1 over 1/4. It goes to 4. So the function is kind of spiking up as it's approaching 0, and then slowly coming down, smoothly like this, right? That's what the function looks like. If I draw this function, just to give you a quick graph, you would have something like this. So, so here, 1 here, this would be 1 half, this would be 1/3, 1/4. So the function would look like this, and then it would go up like this. So this is the function 1 over x. Now, we know the integral of 1 over x, that function, with respect to x is equal to?
Log.
Now